Hello, excuse me.
Online. I didn't switch on my microphone. So now it should work, right? Yes, good. Sorry about that. And now we're going to go on from these simple objects to a little bit more complicated. That is today's lecture, looking at more branched structures and also larger collections of items that may not be clearly isolated. And so what we have, first a little bit motivation, what we are going to look for. Then the two main topics today are skeletons and watershed segmentation. And first, last week, we actually already looked at a lot of metrics, telling the shape, the area, positions, etc. What we now also could look at is, for example, thinking about nearest neighbor. So looking at, we have an item and look which are the nearest neighbors to that item. And looking also on Voronoi tessellation to identify regions around objects and how they are aligned to each other. These can also, of course, also be done in 3D with voxels. And then to do this is we need to actually find a way to how to extract a way to describe the topology of an object. And also, as you saw with component labeling, if you had two clearly nice grains like this, I think I did something with the distance transform last week. We had two grains, they were growing and they're growing. And at some point they were touching, and then all of a sudden it was one item because the component labeling wasn't able to separate them. This is something we're going to look at now. And yeah, that is also related to how the shape of complex objects, how it behaves when it grows. So from last week, we could do the segmentation where we had, actually now I'm cheating because I'm taking the ground truth as you have seen it. Then we can compute the distance map to the foreground or distance map to the background. It gives us some information, but not, let's see, how can I get rid of that one? No, not that one. So, but it's still not maybe telling exactly what we need. So let's look onto something else. Let's see, now it goes on. Yeah. So for example, looking at the practical example here, how many cells are alive? So in this question, you can ask yourself, what are the criteria to tell if a cell is alive? So one thing would be to look at the volume distribution. Smaller cells are usually shrunk and not so alive. Otherwise, you can also see how the shape, maybe the shrinking does some kind of more irregular shape around the cell, not blown up as you would expect it. So then you could look at the anisotropy or some other metric. And how we can do it is, well, you also want maybe to know if the dead cells or the live cells, they are more densely packed. And we could, of course, that's the long time way, is to visually inspect and say, well, that region is more dead, more alive, but it's not, or you can maybe even tell it by the volume or color or something like that. We can also look at the positions, the raw positions. So looking at the centroids and see what they tell us. So for example, if you have more items together, then you can say that they are grouping up more. We can also, that would be another way to divide the image into regions and just count how many cells there is in each region. And then we can compare between different regions or even between different images and see how we can get something out of that. But we need some new tools maybe. Is there a way to find out how many cells there is near a given cell within some radius? Maybe also comparing these regions. So putting it more into quantitative number is what we want to do. And what we want to do is to find a tool that can actually not only do it for a single image or a single series of images, but ideally we want a tool that is flexible enough to be used in maybe your next project or maybe your colleague's project. Then you have something that is more recyclable and saves time in the future. Maybe it takes you a little bit more time to do it that general, but you will have a gain in the future. So looking at the structures, last week we looked at area, perimeter, orientations, positions, etc. But what we want to do is now go beyond that, and with that we are going into the skeletons and the advanced object labeling. And the skeletons or networks is something you see a lot in real life. We can have roads, there's a road network, rivers, roots, blood vessels are typical examples of where you have thin structures that are branching to some degree. Maybe it's not straight lines like in the road network, that's usually quite straight lines. Rivers, they are usually relatively straight, but then when we come to the blood vessels, as you can see here, they're quite curly, so they're not as straight. So it can be very different kinds of structures in these networks. But and the other thing is what we would like to know is which of these networks are connected. That's one thing, and how they are connected. In a root and a blood vessel network, you're not, for example, expecting there to be loops. That wouldn't be natural. But on the other hand, if you look at a river or a street map, you could actually, each city square block is kind of a loop, and also a river. When the river goes around an island, then you also would have a loop in that network. So a couple of things we could look at is, for example, the tortuosity, which is the ratio between the distance between 2 points and how long the path is to get to that point. And that gives you an idea about how curly this network is. Another thing is branching. How much does the network branch? That is general interest for many applications. Actually, I would say all of the ones I showed before. And the first thing we need to do is to reduce our structure into a minimal structure that actually still preserves the topology of the object. So let's looking at this horse. When you compute the skeleton of the horse, it looks something like this, depending on the algorithm. But what you can see is that each point, endpoint here, is actually represented in the skeleton. This one around the tail is a bit tricky, but still it's actually also branches out in several sub details. In principle, you would be able to reconstruct a horse from this skeleton, but sometimes it's a bit optimistic actually. And let's look at some real images. Here we have a piece of a street. So it's an aerial image. You can see the street. You can see that there is a lot of pools around, but the main thing that we are interested in is the street. And in this data set, we had already annotated images. So we have something to compare with. And you can see the red drawings here. Someone nicely did the drawing of the street network. And for our example now, we are just focusing on a small part, not to have too large images and too much detail, but at least we have two branchings and a main street. And the first step to get to the skeleton is to do a segmentation. In this case, we just look at the HSV representation. So it's a color image, and we are looking at the value only, and the value is just a gray level. And the next step is plain and simple, setting the threshold to 0.4, and that gives us a segmentation that looks like this one. A lot of misclassifications, but right now we don't care because we are cleaning it up. And of course, you could use a lot more fancy stuff. You probably would if you are going to analyze many of these images. You can't trust that the threshold 0.4 is realistic in every case. You can have different street colors. You can have different illumination conditions. So you should probably use some kind of segmentation method. Maybe also would be sufficient, but no, it's not. When you segment the kind of structures that we have here, very thin structures, you have a very underrepresented part. So you would have to go for something like the triangle thresholding or Lie or something like that, because it focuses on the small structures in the tail of the distribution. K-means and K-nearest neighbors could possibly do it. K-means, I'm skeptic. K-nearest, more likely. But then you need the training, so you need a data set that tells what is what. So now, as you saw, we had very many structures, and to sort out what we want to have, we use the labeling. And from the labeling, we can also compute the area and saying every item that is smaller than some given threshold is thrown away, or we actually take, in this case, I think we take the maximum object, except for the background. And now we want to compute a skeleton. And the first way of doing it, or I think that was one of the first approaches, is to use a distance map. The distance map more or less maximizes at the distance where you have are the furthest away from the edge. And with that, you can, so let's see that one, I think I need to execute. Yes. And from there, you can see that we have very nicely, so I have first selected the largest component, which was the road. And I compute the street distance map from that. And you can see that you actually have this maximum in the middle. The maximum is not always the same, but it's at least it's a maximum in the middle of the street. A little bit of a close-up. I think there was skipped every 8 pixel. So then you get a map like this, where you still can see that we have a maximum in the middle. And one way of extracting this would be to apply a Laplacian filter. That's a high-pass filter, which focuses on strong gradients. And after applying it, then we need to do some thresholding on this. If the distance is above something and the slope is greater than something, then you can extract your skeleton from that. So here you have a little recipe. This is one way of doing it. There are quite many algorithms to do the skeletonization, and also at different speeds. In 2D, it is quite trivial, but in 3D, you have more complications on the way. So let's look at the skeleton based on this distance transform and some thresholding. And the first thing, we actually compute two kinds of skeletons. One using the Laplacian, and the other one is already predefined function provided in scikit-image. And looking at it, you can see that you have the Laplacian of distance, and it actually pretty nicely focuses on the central line. We need to do some thresholding, of course, but that was part of the algorithm. And the other one would be to do the medial axis. And medial axis algorithm, I think, is an erosion type where you erode iteratively until you have the minimal structure. There are a lot of test criteria to avoid, for example, eroding to a single dot. But the algorithms that are available in scikit-image, some of them you can iterate until a very minimal structure. And the very minimal structure would be a couple of loops. As you can see here, we have a couple of loops in this street map. So you have more or less just thin lines between a couple of loops. That would be a very extreme skeleton. But depending on what you want to see, that could also be actually relevant. So if you want to see how much loops you have and how they are connected, then you don't need all the other stuff, all these spurious branches that comes out. And that would be another one. There is called morphological thinning. And these algorithms, they usually iterate by some erosion principle and looking at the neighborhood. So let's try different things. One thing is you can actually here, you can say in the thinning algorithm, you can say how many iterations you want to run. And then you can also do some opening and closing just to remove some objects. And the first step here is just to thin it a little bit to remove some of the spurious branches. Then by opening, you can remove some of these objects which are not belonging to the main street. And you get this structure here. Then finally, we run the medial axis again, and we get a quite reduced skeleton. So we didn't get all these extra loops here. We didn't get this stuff. So the opening is done using a disk here, disk 1. So that would be just horizontal and vertical neighbors, no corner labels. And that's why we, with the label operation here, can remove this one. So there's a lot of pruning on natural images, as you can see here. And probably you have to, if you want to work with skeletons, you need to find a workflow that is robust for the kind of images and structures you have. And you just have to take the toolbox of different objects. Then, of course, you still have some extra objects, but I think this is quite an improvement compared to the previous one that looked like this. So that one is quite hard. It would actually produce a lot of information that you don't want to see. So after the pruning, it makes more sense. There are some strange regions like around here. That one is a little bit hard to explain. but it's quite an improvement. Now we want to look at, now that we have our skeleton, we want to look at the topology of the skeleton. And things we are interested in is to see how much the skeleton is branching. And we want to actually find the points where we branch. And the trick here is to use a convolution with a 3x3 convolution kernel. And what is happening is if you have just a straight line, then you will get a number. And a straight line, then you have a center pixel and two neighbors, one in front and one in back. And if you rotate, you will always have the same configuration. If you have a junction, then you would have ideally 3 pixels or 4 pixels. And that will be counted because the 3x3 convolution is actually just counting how many neighbors you have, including the center one. And looking at the convolution, you can see here that you get numbers from 1 to 4. And looking at the colors, you can see that the blue one is 2. That would be an endpoint. If you go to 3, then you have the straight line. And if you go to the 4, then you have some junction. So that is a way to characterize the skeleton pixels. And looking at it in more detail, so I just extracted a small region. You can see this in more detail here, that we have the endpoints that look like there's always a 2. We have the straight lines or line segments, there are 3s, and then in the junctions, you have 4s. So that gives us the possibility to then count how many branching points and endpoints we have. And actually, we can create different images. So just by selecting images with the pixel values 2, 3, 4, and actually there is a 5 too, but that's a very complicated area. But the 2s and 3s, they are line segments and endpoints. And then we have, do I have more here on this list? No, I don't. Okay, and then the 4, there was the junctions, and you can see how they also are distributed. A different way, if you want to know a little bit more about the neighborhood, then you can use a smarter kernel. Instead of using a 3x3, you can put weights on each position. And using this as a filter normally wouldn't make much sense. But the idea is you get a binary coding that you have actually looking at the neighborhood in a clockwise circular manner. You can see here, you get the binary weights, and you would get from this kernel, you will get numbers 1 to 511, depending on the neighborhood configuration. And if you are below 256, it means you're touching the skeleton. If you're above, you are on the skeleton line. And this gives, of course, a very complicated image compared to the 3x3 convolution. But the advantage is you can really tell about how, in which direction the branching is taking place. Depends again on what information you want to extract from the skeleton. In some cases, that one is sufficient. Other cases, you need to know more about it, and then you can see here what it looks like. And yeah, so that's an alternative way of showing how to describe the skeleton. You can even, for example, here as one example, you can look at the horizontal lines, that 26, and the vertical lines, they are 21, and then going diagonally down is 20, diagonally up is 17. So you can really tell the direction of how the structure is moving, how the structure of the skeleton is looking. So then we can go on. We may not be happy with the skeleton as it looks. Still, we have small mini branches. So what we can do, we can now, again, going back to the box filter version, we can say that first we extract all the junction points, and then we want to measure the size of the different line segments. And if the line segments are too small, then we say, get rid of them. And then afterwards, we can rebuild the skeleton based on what we have there. And then we can do this kind of segmentation. We have first, we look at the segment IDs. We can see here that we have different segment lengths. And from those, we can say that some of them are not realistic, so we don't want them. And then we can go on and do this as some kind of pruning. You can see that skeleton is getting less and less complicated with these operations. We still have the loop here. I don't think we get rid of that loop, actually. That's not possible. And then we can also look at the width of these elements. And to see the width of the skeleton is a combination where you can take the distance transform and multiply it with the skeleton. Then you have actually the central line or the width, the local width of the skeleton points. And then you can also do color coding, saying that color coding here, that's the segment. Let's see. The maximum width. So you take in each segment, you can just compute the maximum in that segment, and then you do the color coding according to how thick the skeleton are on different segments. So that is another thing you can look at. Often, for example, in root networks, you want actually to see how thick the root is. One thing is knowing where the root structure is, but you also want to know how thick the root is along the branching segments. And yeah, this is just comparison to the end, where we have the pruned skeleton, comparing it to the ground truth, and it looks almost right. We have some of these small streets pieces here that goes out, but the main structure is pretty much realistic. And comparing that to the unpruned medial axis skeleton, which is quite much more complicated. So from this, we can look more about the topology. And now we want to look at looking at these segments. One thing we see here, let's see what's, we can plot it again where we identify, we have the endpoints, we have junctions, and we can plot it together with the image. So that this would be the final product of this segmentation. And you can also see when you now project it on the original image, you can see also why we got these loops. And that's because we have some kind of streak across. What it is, I don't know actually. Some kind of imaging mistake, I believe. And that produces this loop effect in the image. And now we want to see how are these segments connected. And for that, we create a very small skeleton where we have 2 nodes and 2 edges. And after the labeling, we get labeled node 1 and node 2 and label of edge 1 and edge 2. And with this, we want to do some analysis and trying to see which objects are connected with each other to get more idea about how the structure is. And this was a lot of code, which I actually don't want to show so much in detail, but here, the same two images that we had before. We had the nodes and the edges like this. And running the labeling, we get 1 and 2. And now is the interesting thing, is that we do a growing, just applying a dilation. And then you get these edge objects are dilated. And you can see that the edge 1 is connected to this item. No, the node 1 is connected to edge 1, but it's not connected to edge 2. And that would be the first part. And then if you dilate the other one, this node, you would get a very fat block, and that would mean that node 2 is connected to edge 1 and 2. So that is a way how you can combine, see which ones are connected. And that is a very long piece of code, actually. Let's see if it's, yeah. And this is actually a code to do that kind of analysis. I'm not going into it in detail, but it's in principle, it is about doing this growing of the nodes to see which edges it belongs to. And you can see here from the analysis that we have edge 1 that connects with nodes 1 and 3. Edge 2 connects with 2 and 3, and so on. And afterwards, we can actually do a connectivity map where it tells which nodes are connected to different edges. And you can see down here, there was probably some kind of quite complicated thing, but usually it goes over a few nodes that connect together to the same edges. And with that, we can now even do a very simplified network. So this is not the pixel network anymore, but it's a drawing of node to node, not including the edge pixels. So this is already a much more reduced skeleton than we had before. This is just a table more or less with coordinates and connectivity. The width here is depending on the thickness of each. No, yes, it was the thickness of the objects. Then we come to the tortuosity. I mentioned it before, and the tortuosity is the length of the between 2 points and the curve length needed to reach it. And that is relevant for diffusion and fluid transport in porous media, for example, to know how quick the water can or the liquid can go through the medium that it's looking at, and also looking at the vascular tissue, you can see from the tortuosity if something is good or bad in the patient. So looking at our segments, we can see here, I have plotted the tortuosity of different segments. Most of them are quite close to 1, or in the, yeah, more or less 0.8 is close to 1. So it's not curving a lot. And then some, they are curving quite much more. And I think the ones that curve a lot, I think those are the ones that are within the loops. and that gives you a lower tortuosity. And otherwise, we can also visualize it as some randomly organized map. So it's just nodes are colored by the width, and edges are colored by the length, and width sets the. So you can actually do some kind of abstract representation in a network style. This requires a little bit of coding, but in the end, our street network would end up something like this. The positions here, they're just randomized in a way that it still makes sense to show. And you can also use the same to plot the positions here. You can see now that the intensity is controlled, the width is controlled, and also the color of the dots. So you can do these kinds of representations in order to better understand what the networks look like. Of course, it requires that you know the coding. So in this case, nodes colored by the width of the connected items. And then the edges, they are more complicated. So with that, after a while, once you have learned to understand how these are are working, then you can start understanding. It is not always the easiest way to explain to someone else. For you in your development, it may make sense to visualize it in this way. But the more you have to explain to the audience, the trickier it is to use it in publications and presentations. So many of these tricks are very useful locally, meaning you and your supervisor, you understand what's going on. Maybe not even your supervisor understand what you're doing sometimes, because it's too abstract and you have to really explain to put them in the picture of what you're showing. And then we can continue doing some more analysis of the graphs. Here you can see number of nodes we have in this street map versus the number of connected edges. So mostly you have one edge is connected to one node, two nodes. And sometimes you have the cases that would be in the very branched cases, then you can have up to 5 connected edges to one node. That's quite complicated. Can you really? Yeah. So that's the highly complicated version of it. Of course, now I have only shown you the street map, but skeletons are also possible to do in 3D. And the problem with going into 3D with skeletons is that you can, of course, reduce the skeleton to really the very thin case where you only have nodes and you have lines. But very often, when you do this kind of reduction of the structures, you get into planes or plates that are connected in the corner points. And the question is which kind of skeleton you want to produce for your analysis. Some cases, plates are good. Other cases, plates are useless. So then you have to also select the kind of algorithm you use for the analysis. In particular, so for example, a root network, you would not expect to see any planes or plates. On the other hand, if you look into a porous medium where you have pores, then is the question, do you want to look at some kind of medial plane within the pore, or you want to really have the thin connectivity map? There it could make sense to have the plates, but I think I would rather reduce it to doing thin lines and nodes. So here is an example. We have a root network, and the analysis of root networks is, the reason to analyze the root network is, one is the soil stability. Roots, when they grow, they stabilize the soil. Can also be water uptake region. If the root has a certain kind of topology, it's better to take up the water. And also looking at the root growth under different conditions, could be that you have a polluted soil, and then actually the roots avoid the polluted soil, and you can see that from the topology too. And what we are looking at here is, again, segment length, branching, and branch orientation. So if the branches are going sideways or if they're going downwards. Another thing that we also can look at is the influence volume, which is relevant, for example, for the water uptake. So let's load an image. If you look at the root volume, it's not very much information in the single slices. You can see here that you have just some dots in the XY plane. Here you can see even smaller dots of the lateral roots in the XZ and YZ. And this is what it looks like when I project the root network. You can see that it's more clearly than it was on the single slices. And this would be the projection of the skeleton, where you can see the structure maybe a little bit clearer than in this one, where you have some hotspots and some very faint branches. Oops, sorry. So that would be a way to visualize the skeleton of the root network. Now for the visualization, I have actually rotated by 90 degrees, because otherwise it would be very small. Yeah, and here is a detailed view in a volume rendering, where you can see how the different parts are branching. And that is break time.